For part 3, we're going to introduce multiple linear regression. Simple linear regression had one input variable. Now we're going to consider what happens if you put another input variable and maybe another input variable. What happens if you have multiple x variables predicting an outcome? You don't just look at gender, but you might look at income. You look at education, you look at lots of variables predicting some outcome variable. Now I want to emphasize the final exam, it will not cover multiple linear regression, but multiple linear regression is a building block and it's a foundational workhorse tool for all of the social sciences. By far, multiple regression is the most commonly used technique. So this is very important, very useful knowledge as you go forward. So let's move beyond simple linear regression. So far, we've been fitting regression models with a single input or predictor variable x. You might look at using education to predict a person's age or a person's income. But, or for example, Galton's data set. We predicted the height of children using a single combined measure of parental height. The thing about Galton's data set, he also included the height of each parent separately. So here's an idea. Is there we can use the height of both parents separately to predict the height of children. So rather than using a single x variable, this sort of combined measure of parental height, why not say, well, we're going to look at height of the father, height of the mother, and use those two variables separately to predict the height of children. The idea is we're going to use x1 and x2 as inputs together. So we have a model of this form here, okay, when we have one input variable, but we want to use multiple inputs to predict our outcome. So this is what our model looks like when we have two inputs. We have x1 and x2, each with their own slope coefficients, predicting the outcome. Again, we only just have one intercept, just as before. So there's one point in which we want to fit the model through the intercept, through the y-axis. But we now have two slopes. Right? We have two x variables. Just like before, we just have one random error term, however. Conceptually and visually, you can think of multiple regression going from lines to planes. So here we have a simple linear regression line, and then we have a multiple linear regression plane. The idea behind this is that with one x variable and one y variable, you have a scatter plot of data. Right? You have, and you're just trying to fit a line. When you have two x variables and one y variable, you actually have a cloud of points. And what you want to do is you want to fit a plane through that cloud of points. This is just a function of adding another input on the right-hand side of the equation. We're just adding another x variable. Instead of looking at parental height together as one variable, we're saying, well, we're looking at father's height, mother's height to predict the height of children. So when we look at simple linear regression with one input variable, all the fitted values lie on that line. Right? The y-hats are equal to the intercept plus the slope times our x variable. When we look at multiple linear regression with two input variables, all the fitted values lie on that plane. Right? All fitted values lie on that plane. And we're just looking at the fitted values as a function of an intercept and one slope times one x variable plus another slope times another x variable. But the idea is the same. Each data point has its raw y value, and each data point has its own y-hat value. Instead of the y-hat values lying on a line, they lie on a plane. The residuals in the simple linear regression model, they are simply the raw value of y minus y-hat for each person in the data set. Right? These are the residuals or errors. They are how far off a regression model is from the person's raw actual value. The idea behind simple linear regression is we don't want these residuals to be that far off. Right? That's why we want to minimize the sum of the squared errors. When we fit a multiple linear regression line with two input variables, right, we're fitting a plane through a 3D scatter plot of data points, but the residuals have the same form. The residuals are simply the raw values of y minus the y-hats for each person in the data set. Each person in the data set still has one y-hat, still has one raw value of y. Right? The only difference is that the y-hats in the multiple linear regression case are a function of two input variables and not just one input variable. But the residuals are the same, right? You have y minus y-hat for both the simple linear regression model and the multiple linear regression model. How do we interpret multiple linear regression? Well, all we're doing is we're just adding two variables on the right-hand side of the equation instead of just one. Right? Typically, we talk about the left-hand side of the equation in terms of the y, or outcome variable. The right-hand side of the equation are those two x's, or a single x in the case of simple linear regression modeling. Conceptually, with two inputs, we are now fitting a plane through a cloud of data points. The slopes in multiple regression are called partial regression coefficients. With simple linear regression, okay, the slope is a regression coefficient, but in multiple regression models, we typically call them partial regression coefficients because we are controlling for the other variables in the model. The output is largely unchanged in terms of the substantive interpretation, in terms of p-values, t-ratios, confidence intervals, r-squared, with the root mean squared error. It's largely unchanged. However, the slopes have a slightly different interpretation. This is important. The coefficients should now be interpreted as follows. For a particular slope bj, where j is an index from 0 to k, where k is the total number of inputs in the model, this is how we interpret the slopes in multiple regression. For a 1 unit increase in x, we expect the outcome to change by b, holding constant or controlling for all other inputs in the model. Again, for a 1 unit change in our x variable, we expect the outcome to change by that value of that coefficient, holding constant or controlling for the other inputs or predictors in the model. That bolded part, holding constant or controlling for all other inputs, that's unique to multiple linear regression. That's because these are partial regression coefficients. They are coefficients controlling or holding constant for the other variables in the model. We'll look at what exactly that means in just a moment. For the intercept gives the expected outcome when all the inputs are set to 0. That's similar to before, but you just have to keep in mind that if you have multiple inputs, two x variables for example, the intercept is when x1 is 0 and x2 equals 0. So we'll look at and explore a few instances and cases in terms of trying to substantively understand what is going on with multiple linear regression in just a moment.